Welcome back to the system design series. In this one, we are going to design a real-time notification handling system. So this is going to be representative of a system that is capable of processing millions of data points and then sending some form of notification back to the front end to display to the user without any lag to what they're doing on the front end. So this is the general structure of what we're starting with here. So we have an engine front end and a back end, an engine API. All we know is that this engine front end is sending thousands of requests a minute based on whatever the engine RPM is. So the engine RPM directly translates to how many requests are being sent because we send a request per rotation of the engine. So if it's 5,000 RPM, we send 5,000 requests a minute. And that'll encapsulate all the engine data. So temperature, rotation, bore, all that stuff. We're sending that to the engine API. The ask of this is that we need to create a real-time notification system that is capable of processing millions of data points per day. We need to display those notifications to the user on the front end. So an example is if the engine temperature exceeds 600 degrees, we need to send an overheating notification back to the front end. So this is the problem that we have to solve. So in the interview, we don't really need to know what the engine API is really doing. All we really need to care about is that we need to take this data from the engine API and send it somewhere to be processed to look for if in this case the temperature has exceeded that threshold, and then we need to return that back to the front end. You'd be tempted to just make that logic happen on the engine API when it receives that request and then send it back to the front end. The problem is it's not really scalable, especially as we add users and um, increase the RPM. It'll very quickly lag the front end because the front end is is basically sending that request up to the API, and if it lags, if the API starts to kind of get bogged down or lag, we're going to see that reflected um, on the front end because it's going to have to basically wait for that to the request to come back to make sure, to display that notification. So we might see delay in the notifications. So that's not going to work. We need to offload that processing off of the engine API. And the way we can do that is if we introduce a queue. So if we go ahead and add a queue, and I'm just going to make it light blue. What we can do is we can say, okay, once the engine API gets that data, again, we don't really care about what the engine API is doing for the sake of the interview. All we need to focus on is the ask of the problem. Let's go ahead and make an engine queue where we can send all that data to. And so the engine API can do whatever it needs to do, send the data to the queue and then not worry about it and then just continue doing whatever the API is doing. So this way we have now the data going up to the queue and now it's going to sit there. So now we need to register a consumer off of that queue because we still need to figure out, if we need to send a notification. So to do this, we can actually introduce a new service. So we can call this like notification service or something like that. And the notification service can be responsible for consuming messages off of that queue. So the engine API will publish the message to the queue. The notification service can then consume that message off of the queue. And what this notification service needs to do is it needs to somehow send that data back to the front end. And the way we can do that is not with REST APIs because there's nothing to request on the front end. We can actually use WebSockets. So WebSockets will allow us to create a socket, allow the front end to open a socket uh, to the back end. So basically, there will be an open connection from the client to the back end where we can send one-way communication from the back end to the front end. So there's no awaiting any kind of response. So if we just call this, we'll just make this a WebSocket little tag here. So we can send the WebSocket notification back to the front end. So now what we've introduced here is we've introduced a flow of data where our engine front end has already been sending data to the engine API. There's no performance there's no performance implications there. Um, that's one of our assumptions, is that this engine API is functioning. It's functioning well. It's able to keep up with the ask of million message points per day. So we're not concerned about that. All we need to add is the additional functionality of the notification processing. So what we've added is the queue. The queue will get our engine data. Then the notification service will read off of that queue and then send that notification back down to the front end via WebSockets. So this is actually a pretty good solution. It's scalable. The engine API is not awaiting anything by sending it to the by publishing a message to the queue. It's not going to introduce any little to no latency by publishing it to the queue. It's near instantaneous. The notification service is going to have all the work to consume the messages off the queue and make the determination based off of what whatever we're looking for, in this case temperature, and then send that back down the front end. So with this approach, we're going to get basically near real time notification handling. And the reason why we had to separate the notification service from the engine API, we kind of went over that. But if you think about it like this, if we need to scale up the notification service, if we need to introduce, make the instance bigger, if we need to introduce two running instances of that and then load balance those, we can scale the notification service independent of the engine API. So if the queue, if for whatever reason we need to increase, like, maybe check for an additional notification or something like that, or if we need to do something additional to what the data coming from the engine API, if we need to introduce any additional functionality there, what we could do is add another consumer off of this queue and then add another service to, let's say, check for something else and then send that back down the front end. This will work if we introduce an exchange. So an exchange, I'll explain in a second. I'll just do a little, I don't know, what should we do? A little triangle? A little triangle, I guess. I don't know. Well, I guess I'll be specific and call it a fan out exchange. Oh, what happened to my text? There it is. All right. Okay. So, whoops. This is the setup here. And then the message will get routed to the queue. There we go. And this is, hold on here. This is going to get a little weird. All right. And then let's create another consumer. And let's drag this here. And we'll call this, like, I don't know, we'll introduce like a logging service or something. Just completely hypothetical. So let me kind of explain what's happening here now. So let's say the reason why this is scalable is because if we introduce separation between the notification service and the engine API, we already get basically independent scaling out of the box, right? Because we can scale up the notification service independent of the engine API and vice versa. And because we're using a queue, there's going to be little to no latency. And my assumption is that we're going to be using RabbitMQ. We could send millions of messages to the queue, and this consumer on the notification service would consume those. I mean, just incredibly fast. RabbitMQ, at least the AMQ protocol, is just unbelievably fast. So we're going to get extremely fast, almost near real-time notifications going to the front end. But if we need to add additional processing of that same engine data and do something else with it, maybe we're doing really, really heavy logging or need to, send it to a database or do whatever with it. We don't want to make the engine API publish to two different queues with the same data. So we can introduce what's called an exchange. An exchange is in RabbitMQ is a thing that routes a message to a queue. So when you publish a message to RabbitMQ, you're publishing to an exchange that then is the message is then routed to a queue. There's topic exchanges, there's fan out exchanges. A fan out exchange is an exchange that will route to any queue that's you've set to be binded to that exchange. So the engine queue is bound to the exchange, and I have to change this. Hold on, we'll do a logging queue or something. So the logging queue is bound to that exchange, and the engine queue is bound to that exchange. They'll both receive the same message that is routed because that's how fan out exchanges work. So this way we can just continually either adding queues to that exchange, which will introduce a little bit of latency in terms of the routing. As long as we keep the routing not complex, like we don't start introducing uh, very complex keys or anything like that. A fan out exchange is lightweight because it just publishes to everything that's binded to it. If it was a topic exchange and we set a key on the route, then it might take a little bit longer. Um, but this works and this is scalable. We can scale anything independent of anything else. Um, but it's nice because the engine API is not going to be impacted in terms of performance. The front end will receive its notifications, so we solved that part of the problem. But we've set it up that way we can add additional complexity to the system and not impact existing functionality, which is very important. So I think we satisfied the ask here. We set up a system where we can continue to add features and enhancements to this and not see any impact to performance. And again, we get everything kind of that comes included with queues. If we set up the code correctly, we can just continue adding more robust features like we showed in the last system design video with error handling and retries. So you can imagine if we add a retry to this queue, we could really make this a robust system if we remove any kind of error situation on the engine API and we just use queues. That way the data is preserved. We can retry it and we can get real-time notifications. So anyway, that's it for this system design series video. Hopefully this made sense. Let me know if you have any questions. We will get into the code of this um, for this setup in the next system design series video. Um, I'll probably limit the code to just the real-time notification processing. I don't think I'll add the logging service and the logging queue, but I'll show you generally how this would be structured and set up.